So I'm a senior lecturer at UNSW ADFA. I'm actually not a world-leading AI specialist or anything. This is a work from my PhD student, Shahryar Shakir Samit. I asked him actually to present it, but he was too shy to come. And he has like 8 papers that he's working on that he's trying to submit. So I didn't want to bother him on the weekend. Okay, so I'll be talking about a work that we've done a while ago that has some promising outcomes for any AI systems, but it's in no way a substitution to what's already available. So we called it HOD Light, Human Object Detection, light version, and it's about reducing the computational cost of such systems. So the everyday problem for an AI is that it must see people instantly. So otherwise your self-driving has no safety features. So what we'd like to know is that whether there's a person in the scene, and aside from other objects. Now. The imaging system that we're all familiar is basically our eyes that sense the image, and then our brain is the interpreting device, and then we decide whether there's this human or not. We're basically biologically wired from childhood to pick up things because we work in a similar way. We obtain information, repetitive information, and then that gets written in our neural net. In an actual scenario, a person could be far away. The scaling could be different. The lighting could be different. Everything could be is against us basically when we image around. And a useful detector has to be fast and accurate. So. What do we mean with fast and accurate? Well, humans' cognition and reaction times are around like less than 100 milliseconds. I mean, anything above that we will perceive. So think about, for instance, if you're talking on the phone, and if the signal's bouncing off a satellite, a geostationary satellite is like 36,000 kilometers away. So that's like about that time lag. So the return time, you might be able to actually pick it up sometimes when you do international calls. And if you were to talk to someone on the moon, that's 1 second delay both ways. So that you would pick it up. But anything below 100 milliseconds, it's very unlikely that you pick up any delay. So all our conversations here happen below that threshold. And what we want is real time, and what means that we don't want any calculations, anything happening after the event, which becomes completely useless. So if we can, we have a budget for doing all those processing within 10 milliseconds. If it's over that, like capturing the image, interpreting it, and acting on it, is more than 100 milliseconds, that's useless. So the technological counterpart for the sensing device is, to the eye is basically the camera. And then we have the computer, and then it loops back to this box where we have to decide what we have on the scene: humans, trees, buildings. Okay.
Jenny, are you going to fix that?
It's not your phone.
No, it's on the
No, I'm asking for the
at the crack of the house.
Okay.
I know it's plugged, I just wonder whether it's connected.
No, I don't think so.
Let's get there.
No, we must listen to it. Okay. So that's okay. So then our imaging to action workflow becomes we have the camera image for our system, and then we have the AI vision system. And our main aim, because our topic is about detecting humans, are there humans in it? So detected or not, and then we have to have some action. Now the action part, we're not concerned. We're basically concerned about the human detection part from the camera image to that box. I mean, in our work. So say I'm going to give some idea of how things work in an AI system. So say we want to classify 3 objects. So that means that the output is one of those 3 options. So the way we start is by training the system. So we have a deck of images. In this case, lots of images containing humans. Okay, and then we apply, each of those boxes have been a PhD or multiple PhDs before, so I'm not going to go into the details much. But feature extraction is picking up on things that are recognizable on images. So each deck of human images, in this case, like maybe hundreds of thousands of them, they get feature extracted. Now, the feature extraction could be done manually or automatically. Now, the earlier systems, you would pay people to actually sit in front of a screen and box features, saying, okay, this is a human, this is a cat, this is a dog, etc., or and this is an object. So we will need a training data that contains all the metadata, that contains the truth information, so knowing what we're looking at. So when we feed these into the algorithms, they will start a classifier space. So it could be a 2D map or 3D map or n-dimensional map, and say that, okay, this image has features that lay into this area. And then, because we're trying to test for 3 different objects in this case, we would also have a stack of dog images, like different dog breeds at all different positions, etc. And we just feed it in and do the same thing, and that will create us another classifier region. And with the cat images, same. So we get another region, and then when we feed in a test image, that will look at different features on the image and say, okay, this part is 0% human, this much percent dog, or whatever, like, because there are 3 options. And then when it looks at an area that has the human, it will probably detect the head, other features like arm, legs, etc. And then decide whether it fits in one of those regions. Okay, so all those things are done in the background, obviously. And when it realized that, okay, that fits in one of those points, then it says it's a human. So that says, okay, we found a human in the image. Now, the way these feature extractions work is, as I said before, we have an input, and then someone actually labels them manually, okay? Saying that, okay, this is an image that contains, okay, 2 human beings, different size. There is a cat. There are 3D objects. So the more information we can feed in, the better. But if it's solely aimed at picking up humans and or known objects that of interest, we just label them as such. But bigger data sets, they have all sorts of information which are more useful for training these things. So that gets fed into the classification network. So that those dots are actually like pixel values. So even though I've shown here like 3 by 3, that's actually how many pixels you have here. Say 100 by 100. That makes 10,000 input values, and then you have these outputs that would probably connect to another layer that has only 2 options, human or bird, for instance, in this case. And the way the neural network works is that it starts with random numbers in it, and then said, okay, this was a human. And it makes sure that by back-propagating the information, say, okay, these values should be this. So how do we get to these values by changing the biases of these of these nodes, so that when we feed this image, we get human, bird, or whatever the truth information is. So that takes that's the training bit. We call them each step an epoch. So every time it tries to readjust all those things using some clever maths, optimization mathematics, and then when we feed actually this picture, then there's a cost function actually. So every time we try to change those values, the outputs will fluctuate into, okay, human, bird in this case, then it'll give us some percentage. And we set some threshold saying that if this is a picture of a human and the output says like 90% human, that's good enough. If it's 89, keep trying, right? So it keeps trying to readjust those numbers, and then you have the neural net. And this is done for every single image of humans, so it's not just for one. So we feed in, say, 1,000 of them. We have to readjust all those numbers until all those 1,000 of them actually give you a percentage of human that is like 90%. So that's a very computationally intensive process. That's why we use GPUs, graphical processing units. And so like 20 years ago, you could only use processors, and they're quite bulky and power hungry. But then GPUs, graphical units, they just do very simple arithmetic in big quantity, so that made things go faster. So the next thing is deep learning and convolution neural networks that actually put those feature extraction and classification cases together, so that gives you a deeper neural net. And the process is similar, but it works on a larger scale. And then you get the output directly. So the classification part is embedded into the system, but I'm not going to go to the details of it. So so they became quite popular, and then sped up the training processes. So how does it basically relate to the Tesla full self-drive? So the Tesla system are not proprietary architecture, so we don't know exactly what's in it. But it's a very vision heavy. Like Elon Musk doesn't want to use LiDARs for good reason, because that can interact. If you have like all the cars having LiDARs, they will be basically blinding each other. Whereas we're not blinding each other by just looking at each other, right? So vision doesn't work that way. So passive system has extra a lot of benefits. LiDARs do themselves as well, but they have to be by themselves. Like if you have one LiDAR working around, that's great. But if you have 10 LiDARs working at the same time, they risk blinding each other. Like that, you're not going to be able to find different frequencies for each laser, wavelengths for each laser, that many different ones. You want to make them cheap, and you want to make them widely available. So they will definitely interfere with each other. So it's a very vision-heavy stack. And it's not a simple one simple AI model. If we look at the some of their publications, we can see that there are lots of networks working together. So one bit picks up on say humans, one bit picks up on figuring out what's the 3D surrounding is. So it builds those different models from those the camera images. Like the most interesting one is the bird's eye view. Although it would be nice to have it on the screen, it actually has it. We don't see it. Like, so that from the bird's eye view is that you have the car in the middle, and then you have the road layouts, 3D objects, and humans, obviously. But that we don't see that. But the processing in that is done on those vector images. So first there's a layer where it determines what's what, and then there is another layer saying, okay, what I'm going to do now, or many other layers. So these actually go up to like 48 networks. So it's just not one, like not just one, and it all has to work on the same system, and with it that 100 millisecond time budget. And then they reckon it takes like 70,000 GPU hours to train them. For every time they release a new version of it, that's a lot. So that's a lot of GPUs. Of course, they have probably a farm of them, and that's why NVIDIA's price goes up. So we don't know the exact architecture, but it's probably something like this. Obviously, we have the cameras, video streams coming in, the neural vision encoder, 3D scans, scene understanding, so figuring out what's what, like lanes, signalization, and so on. And then there's the planning part, and of course the driver supervision. So the next step is probably trying to get rid of the driver supervision, or it could be also interpreted that it's also like checking what the driver is doing. So it's not just what it's sensing in its surroundings, but it's also monitoring what you're doing with the steering wheel, because if you let it go for too long, it will start penalizing. So where is that our work fit in this? So it's a one compact specialist system in the larger scheme. It's not a driving stack. It's not going to replace any of those components. It just it can actually make it work better or on a lower budget systems. So it has to do, like as I said, figure out lanes, signs, depth, vehicle, pedestrian, cyclist, everything that's involved in a traffic situation. It has to be able to pick up those things and decide what's happening. So when it's picking up moving objects, for instance, it should calculate whether it's going to intercept you or you're going to intercept them. So all those calculations have to be done on the fly. But those are done actually deterministically, but all the other detection stuff is all machine learning based. So it's not a driving system. It does not replace it, the FSD. It's just one part of it. And our aim is to basically detecting humans efficiently. Of course, detecting, it also involves about optimizing the system. So currently we're aimed at detecting humans because we're working on human data sets, but it can be anything. It could be bird, it could be wildlife, it could be fire, or anything else. So, so in a Tesla-like system, that could be used as an extra layer that increases the safety of the system and add extra features. Say I'll come to that a little bit later. So the value of the method is that to search for efficient design, train a smaller model from a larger one, then prune unnecessary parts. So when I showed you that neural network, that takes a lot of memory, that takes a lot of processing power. But if we can achieve the same functionality with a smaller one, we could either run another network next to it or run that one faster, right? So it's basically budgeting time and effort and quality. So in a lab, normally we're looking at best results, accuracy, and so on. But in real life, that's not enough. It has to be fast enough as well. Because as I said, it has to work within that margin of real time, 100 milliseconds. If it doesn't do that, it's not useful. It's like sleeping on the wheel, basically. So what large models have is that they have great accuracy, but they could be bulky. So you may have to run that system on a very large GPU, whereas the onboard computer is always limited. So I was interested in at least leasing the FSD, but my onboard computer is the one generation before, so I can't do that. So that also prompted me, maybe we could have something like that, can use older generation computers to run new software. So limited by not just processing power, but also limited by power drain. So the more intensive calculations you make, the more all those go up. So what we need to have is real-time decision, no waiting, which is that under that 100 millisecond. So what we really want is high accuracy, because we don't want to have false alarms, either negative or positive. We want fast response below that threshold. And we'd like to have a small memory footprint so that either we can run larger, more interesting or more features on the same hardware, or run it faster. So these two things go hand in hand, opposite direction actually. And low computation. Now, what we end up having normally, what happens is that models get bigger because you train it on a different data set and it gets bloated. You want more features, more accuracy, the model gets bigger. More compute, obviously, and more latency. That makes it harder to deploy as well, because your next neural net, if it doesn't fit on the existing hardware, you're not going to be able to deploy it. So when we get those on-the-air updates, they work hard at making it fit into the existing system. So our goal is basically to keep most of the intelligence while removing the excess computational time or requirements. So I could use like computational weight requirements. Lightweight system have less computational power. So we'd like to be able to achieve what a large model does with a lighter system. Okay. So this human object detection light, as we called it, relies on a system where there's a teacher model, or teacher-student model, where we have a neural net that actually does all the things we want, but maybe not fast enough, right? So the large model is not necessarily fast enough, but it does what's required. Like, it's accurate, it does what's needed, but maybe a little bit slower. Or the existing one might be all right, but the next one might be a bit slower. So the student model is a model that actually runs this. So this is the system that we're working on, is that it runs the large expert model and learns from it and generates a smaller neural net. Now, you can think of, okay, what's the difference from training the large model with the same data and then train the small model with the same data? What's the difference? Well, the difference is that the large model, it has the raw data input, whereas when the student model actually runs the large expert model, the expert model also tells things like, okay, this area of the screen is like 90% human, this portion is 90%, I don't know, stationary things. That extra information allows the student model to learn better. It's like having a tutor, basically. The teacher one is the expert who learned that by themselves, but then the student model can achieve the same accuracy and even sometimes well, faster by learning from how the teacher model actually works. Okay, hope I'm not mixing those things. So once we have the student model, we test it, checking which one performs better. So there's an iteration loop where we generate a student model, we test its performance, and of course the aim is to achieve at least as accurate as the large model and make it faster. And then there's also another stage where there is pruning, which means cutting off actually neural net components. So you saw all those dots. So we have 10,000 input. That's fine, but in between there are layers of neural net that may be removed without losing any accuracy, because and that's iterated again as well. So the idea of pruning is after learning what's happening. That means that, okay, it's like basically a scientist doing all the experimentation and then writing a book, and then the student reads the book and doesn't spend 20 years figuring out one single theory. So they learn the theory and then keep going. So the pruning bit is like, you don't have to do all that experimentation, but you retain the knowledge of how to perform the required task. So we call this technically neural architecture search, NAS, plus feature level knowledge distillation, FKD, and structured pruning. So the overall pipeline of this is, so we have the input image, and then we have a genetic-based architecture that's the bit that generates the large model. And then we have a student model that learns from the large model. And then we do some optimization on the different student model. It's just not one student model. We will look at which iteration of the model performs best, and then go up and do another feature level knowledge distillation. So again, learning what parts did what, and then decide on what to retain. And then run another student model there and back and forth with a structured pruning, because we might have cut off some branches that shouldn't be cut off. So go back again, and can it work with the cutoff? If it doesn't, add some more or subtract more. Of course, we don't want to complicate it. We just want to reduce the complexity every time. And then come back and do some fine-tuning with further knowledge-based feature knowledge-based distillation. So these are quite. It gets really technical if we want to go any deeper. But the process is that you start with a large model that already trained. I mean, we could be starting from zero, or we could be handed in a system that has the large model, and then we can apply all these steps to obtain a final detector that is lightweight compared to the original one. And then we can detect the person. So these are also flowcharts and for the describing the process. So I'm not going to go into deep, because that would probably get lost as well, because my students work. But this represents more what's really happening. Say you have this is the pruning bit. You have the neural net. You have all those connections, even though we showed only one layer. But that's the bit that we're getting rid of to get the same output. So instead of having this large network, we're just little by little pruning away the unnecessary connections. I mean, how do we decide they're unnecessary? We just remove one and then try what's the output, and then try to retrain it. And then that takes a while. And the knowledge distillation is where we have the system with its internal feature pyramids, so that each layer of the network basically picks up on a different feature. So one might be picking up on heads, or it might be picking up legs, it might be picking up on, they could be at different scales as well. So low resolution, medium resolution, higher resolution, because the imaging system doesn't know the scale really. You could be far away, you could be close by. So it's not just one feature. It will pick up on all those at different levels. And then it will look at intermediate maps and decide which ones to retain. So the teacher large and accurate model, we obtain the feature maps. Feature maps are actually what it notices. So you could think of that like heat maps. Each of the features say, okay, if I look at the feature map, it says, okay, here is 90% human, here is 90% tail, here is 90% horse, here is 0% human, 0% horse, etc. So for each of the layers, like horse layer, human layer, and sub-layers like head layer, leg layer. So those are all internal maps that show like contours. Some of them could be picking up on straight lines. Some of them could be picking up on curved lines. And so those are all the feature maps. And they are basically obtained through the training process. So the student model ends up learning what those things are noticed, and then it scales down into its own network, and then try to achieve the same output as the teacher model. So what we basically achieved is that the small model keeps strong accuracy while becoming much lighter and faster, and that's the aim. So the smaller model ends up having like, in this case, like 84% fewer parameters, lower flops than teacher, so 26 times or 27 times less. Frames per second doesn't mean anything without comparing to what the other one was, but it was like 80 or 60 frames per second, where this can do 122 frames per second. And the average precision that it achieved was around 83, which is pretty much the same as the large model. Now, we also tested this on edge computing devices like the Jetson Orin Nano, if you're familiar with that. So we ran it on it, and it ran faster than running it on the actual GPU. So we achieved these indices. So relative computational burden. So if we say 100% for the original teacher model, the hot light achieved 16% of that computational burden. And for reference, I also put the data sets we used. So if we were to implement this on a Tesla-like system, again, it's not a replacement. It would provide fast pedestrian detector for vulnerable road users. It can compress compression of recipe for perception network, so it could do more with the same hardware, and it could be just running as an independent watchdog, running as a separate code in the system. So why does it matter for vehicles? We want lower latency to keep that time budget. Lower energy use. We don't want to overheat things. And if we want to do more, we can do more with the same chip budget. Right? So if we're fine keeping the same consumption and energy budget, we can do more with it. It will help most with pedestrian, cyclist detection, because those are the main hazard on the road. It will reduce the power consumption of the systems. It could also be used on drones that can actually do the human detection themselves instead of streaming the data to a data server. They could actually, like rescue drones can be roaming around and then say, okay, I found a human, instead of sending the video and then the center crunching the numbers trying to figure out whether there's a human there. So like in disaster situations. So what it's not doing, it does not solve planning, control, fleet learning, or full autonomy by itself, but it actually augments the existing human detection side of it. So what we would need for to be able to deploy it, obviously, we'd need more data on more noisy environments. So we use the data that was available online because it's very difficult to get, well, not difficult, but to get large data set with humans in them. It's ethics approvals. So we all, and for benchmarking, we used common data sets available online. But of course, Tesla records a lot of usage. Therefore, they're gathering all those data. That's why it gets better and better every time, because it's accumulating all the data. So so more data is needed. Run on multi-camera systems. We just use monocular, so just one picture. We didn't work on large system that mosaicked all the surrounding cameras. That would be helpful to optimize the system on hardware, and that would also give us safety case, edge cases. Like edge computing means doing the computing on the field, in the field. So it could also give redundancy. So safety systems always nice.